Yeah, thanks for the introduction, team. Hello, everyone. I'm Diego Caballero, and yeah, let's talk about vectorization and scalable vectors in MLIR. So I'm going to start talking about the representation that we use, basically the Linalg and the vector dialects. This is something that is not new. It has been presented multiple times, so I'm going to go quickly over this. We have a bunch of links at the very end to pass presentations if you want to learn a bit more. Yeah, let me provide a bit of context on the compilation tools that we use for this work. Obviously, we are using MLIR. So here you can see most of the dialects that we use in our compilation flow. Today, we're going to focus on Linalg and vectors, and also on the two new dialects that we introduced to model SVE and SME. Regarding the compiler drivers that we use the ERI ML compiler, which is an end-to-end compiler using pipelines and passes, similar to what we have, for example, in LLVM. And we also use the transform dialect, which is an intermediate representation that we have in MLIR to describe optimization strategies and how to apply them to specific operations. Really powerful if you want to iterate and try different combinations of optimizations quickly. So moving on to Linalg, as you may know, Linalg introduces operations that try to preserve as much as possible the high-level structure of the computation. Here we have a few examples. It works on tensors and memrefs. We mostly use it on tensors because it's far easier to reason about things like data dependencies and other stuff that we need in some of the transformations that we apply. And again, we have a few examples here. You can see a Linalg generic. You can see all the structure traits that we encode there. We have indexing maps that are very helpful to understand the memory access pattern of the input and output tensors. We can get information about whether a dimension is parallel or reduction. Yeah, all this information is something that we leverage a lot during the vectorization process. We also have what we call named ops, as you can see on the right. Basically, if there is a computation that we cannot represent very well with a Linalg generic, we introduce a specialized operation just for that. And we have a bunch of them, like we have a matmul here, convolutions, we have pooling, and quite a few others. About the vector dialect, again, this is not new. A couple of things that I would like to highlight. The most important one is that we have multidimensional, we have representation for multidimensional vectors from the very beginning. So we can represent things like matrices or even higher rank vectors. Here we have a couple of examples, like a 2D vector and a 4D vector. And we use multidimensional vectors even if the target doesn't support multidimensional vectors. It's only, for example, 1D. This representation is very convenient, especially to model operations that are naturally multidimensional, for example, like transposes. And this allows us to optimize them properly. Also, we have a couple of level of abstractions in the vector dialect. The high level one is focused on preserving the structure of the computation, similar to Linalg. And also, we model computation in a more abstract way. For example, here we have a vector contract, which is what we use to vectorize a matmul or a convolution. Basically, we are reducing. It's an operation that computes a reduction across some of the dimensions. We have a transfer read, which is a high-level vector load. And we have a vector mask that is the mechanism that we use to apply vector masking to any operation in MLIR, even outside of the vector dialect. On the low-level side, we have operations that are closer to the hardware, similar to what we have in LLVM. We have vector FMAs, vector reductions, shuffles, structs, inserts, and all of that. But the main difference with LLVM is that we have support also for multidimensional vectors here. So now let's talk about the vectorization approach that we follow, that we have on Linalg. As many things in MLIR, we also follow a progressive approach to vectorization. These are the main steps that we apply. The first one is vector level tiling. And here, the only thing that we do is to apply tiling using the vector sizes that we want to use for vectorization. We don't generate any vector code here. The main goal here is to generate the vector loopness that we're going to end up with after vectorization. At this point, we also apply some transformations like padding or peeling, basically generate a reminder loop to deal with number of elements that may not be multiple of the vector lengths that we are using or the vector sizes. And that's all, no vector code here. So then we move to step number 2, where we apply vectorization properly. We call this the Linalg Vectoriser. And here is where we leverage all the information that we have about the Linalg operations, the memory access pattern, and all kind of information to generate the vector code. We have multiple vectorization paths. One is the generic one, where we try to do our best with the generic information that we have. And we also have different ones that are more specialized for operations that are much more difficult to vectorize efficiently, like, for example, convolutions. Then in step number 3, we lower the high-level vector operations that we generated in the previous step to lower-level operations. We apply a lot of canonicalization patterns to try to improve the performance of the vector code. And we also start introducing hardware details. We also start introducing transformations that are a bit more hardware dependent. Finally, in step number 4, we legalize the dimensionality or the rank of the vectors. If we have generated multidimensional vectors and our target only support 1D vectors, then we go and enroll the dimensions that we don't want to map to the physical vector register, or we generate loops also for that. So let me go quickly over an example to illustrate these steps. I'm going to use a Linalg matmul that is running on tensors and with dynamic shapes. So in the first step, we apply vector level tiling using the vector sizes. As you can see, we want to vectorize using 8, 32, and 1. So you see how we have introduced basically 3 SCF4s that are doing the tiling. And no vector operations at all. We still preserve the Linalg matmul. The only thing that we do here is to extract the slices of the tensors that we're going to process for this particular tile. And then we pass those to the Linalg matmul. Then in step number 2, we vectorize properly. Here we use masking to deal with the fact that we don't know the number of elements at compile time. So the first block of instructions that you can see there are computing the masks that the rest of the instructions are going to use. Then we have some transfer reads that are basically loading 2D vectors from the input tensors. And then we pass those 2D vectors to the vector contract that is computing the matmul itself. And then we apply masking on top of that to make sure that we only compute the matmul and especially the reduction for the elements that we should based on the runtime information. Then step number 3, we lower the high-level vector operations. In this case, the vector contract, we lower it to a vector outer product, and then we lower it again to an FMA. You can see all these transposes and extract and broadcast. This is mostly to change the data layout within the vector and accommodate it to the new requirements of the vector instructions that we want to generate. And finally, we legalize the dimensionality of the vector. So we had generated 2D vector loads. And here, assuming that we only have support for 1D vectors, we decide that we want to map the innermost dimension to the physical vector register. And then we enroll the second dimension. You can see, the indexes that go from 0 to 7. Okay, so that's all for my side. Here you have some instructions in case that you want to give this a try. That's how we compile models with theory. And also you have an example of the transform dialect with a strategy that is basically computing or applying tiling and vectorization to Linalg matmul. Really easy to extend and to try different things quickly. Now, my colleague is going to continue.
Thank you, Diego, for this lovely overview. So we tried taking this vectorization technology and apply it to some new emerging architectures, namely those implementing scalable vectors and scalable matrices. So before diving into that, I'll give you a very quick introduction into scalable vectors. I think it's really helpful to use a specific example, and me working for ARM, I'll just use and refer to scalable vector extension. So that's the technology we have, and I'll contrast that with Neon, which is our fixed width SIMD extension that a lot of you might already be familiar with. So with Neon, you have vectors which are 128 bits wide. So you know that you will, when you write your compiler or write your code by hand, you will optimize for that. And it's, I think, all very quite well established and understood technique. Now, this hypothetically becomes problematic if you decide to extend your ISA or your SIMD extension and introduce wider vectors, new instructions, and suddenly you have to update your compiler or update your implementation if using intrinsics. And then again, if you extend it again, then you have a problem. So one way to work around it is introduce scalable vectors instead. And in the case of ARM's SVE, we just say that your vectors are at least 128 bits wide, but it's in fact a multiple of that base size. This multiple within compiler land is referred to as vscale. And vscale can be 1, can be 2, can be 4, can be 8, can be 16. And the example on the slide, vscale is 4, so your vector is 512 bits wide. One important thing about vscale is something that you don't know at compile time. You don't know the value. You do know the value at runtime. What's also very important is that this SVE enables vector length agnostic programming, which means ISA is designed in a way that allows you to write assembly that doesn't need to reveal the vector width. And on the example at the bottom, you can see some for loop on the left-hand side and assembly on the right-hand side. And the assembly doesn't really show how wide your vectors are, and it just works. And that's key. So I already mentioned vscale. Vscale is a very important part of this. I said that it's not known at compile time, but we have access to intrinsics in LLVM and MLIR that gives us an SSA value that we can use in compilation, and that's really what we need. So even though it might sound a bit scary and enigmatic, it's actually pretty well supported. And scalable vectors are already well supported in LLVM and MLIR. You have two examples of how to define scalable vectors in LLVM and MLIR respectively. I'll focus on MLIR. In MLIR, we simply use square brackets around sizes that we want to be scalable. So that's what we'll be using moving forward. Now, I'll go over the examples that Diego presented, and I'll show you what changes when you want to do scalable vectorization. So this is step one, tiling. We need to make sure that tiling is scalable. So you can see the middle loop is now updated, and this step is simply multiplied by vscale. So that's at the very top. And that's pretty much the main thing that has changed compared to what Diego showed earlier. Otherwise, it's similar. Next step is loop body vectorization. So again, it's similar code that Diego showed earlier, but this time vectors are scalable. So you can see there's a lot of dimensions that are now with square brackets. Obviously, you need to make sure that it's the right dimension that's being made scalable, because these are multidimensional vectors and you can't just make all of the dimensions scalable. So that's one tricky part. But otherwise, the framework is flexible enough. Like, there aren't that many changes in this example compared to what you saw earlier. The framework simply is flexible enough for us to get support for scalable vectors almost immediately. I should mention that you see vector mask and vector contract. You need to make sure that these operations support scalable vectors, so there is some work to be done. Also, there are other vector operations, and there's a lot of canonicalizations and other things that need to be updated. But the framework is already there. So let's take it one step further, and let's look at scalable matrices. And again, I'll use an example from ARM. So ARM has introduced scalable matrix extension. And scalable matrix extension is really like a extension of SVE. The good way to look at it is it starts with SVE and SME builds on top of SVE. Main thing that SME introduces is the ZA accumulator. So it's the big square storage array, which we use for matrix multiplications because they're very important. One very important aspect of this accumulator is that you, at say assembly level, you get access to so-called views, and you can view those virtual tiles. And you have an example on the right-hand side where the ZA storage is split into 4 virtual tiles. Now, The tricky part is that the number of these tiles and their dimensions, they depend on the underlying element type. And I included 2 examples for I32 and I16s in the array, in the table that you can see on the slide. This is key because we will not get any help from the backend at the moment to allocate these tiles or to make sure that we use all the tiles that we have access to. It's something that we need to take care of at the MLIR code gen level. So that's one of the challenges that comes with this. I also mentioned that we call it ZA accumulator because one very important part of SME are outer products instructions. And these are important because you can decompose a matrix multiplication into a series of outer products. And there's an example at the bottom of the slide of the MOP-A instruction, which is a outer product instruction. The output accumulator is the first register that you can see, ZA0S, and then 2 predicate registers for your input column registers at the end, Z1 and Z3. So in order to support SME and MLIR, we introduced a lightweight dialect. This is just a quick overview, and a lot of it is still work in progress. I split the ops into regular ops and virtual ops simply to make it a bit simpler. Regular ops usually map quite nicely onto instructions that we have within the ISA itself or a series of instructions. Virtual ops are more like they get folded away during lowering and they simply facilitate all the infrastructure that we need and just make things a bit easier. LLVM intrinsic ops, they usually map, they do map one-to-one to actual instructions. We also introduced a few function attributes and passes because one very important aspect of the ISA is that in order to target SME and to use the ZA storage, you have to disable it. And that's something that, again, we have to take care of inside MLIR, but I'm not going to cover this today. So going back to the example that we've been going over, this is, again, a matmul. On this slide, I combined 2 steps, tiling and vectorization. And I'll just highlight what has changed. So in this case, we have 2 loops that are tiled using scalable sizes because we have scalability in 2 dimensions. So that's pretty straightforward. Various vectors are also scalable in 2 dimensions. Again, you need to make sure that it's the right dimension that's being scalable. And other things that I want to call out is also the fact that vector dimensions, they map much perfectly the dimensions of the virtual tiles. So that's what I mentioned, that we have to take care of that. We can't rely on anything further down in the compilation process to split things for us, so it needs to be correct at this level. We have also, we also keep vector outer product at this level. Diego mentioned that this can be lowered further to lower vector operations like FMA. We don't want that because SME has support for we have outer product instruction and we want to use that. Which brings me to the next slide, which is taking all the 4 steps and then lowering further down to the SME dialect itself. So again, this is your matmul. You can see 3 SCF4 loops as we had previously, but this time the vector outer product is replaced with the intrinsic, SME intrinsic, that does outer product. I highlighted all the arguments that you passed to the intrinsic. They map one-to-one to the example that I showed earlier using assembly. The first argument is the accumulator, which is I32. So we have to specify which virtual tile we want to use. And that's one of the big challenges that we have. We can't really rely on the backend to take care of that for us. I also highlighted 2 SME instructions. ARM SME tile load, that's fairly straightforward and simply loads into a virtual tile from memory. The following cast vector to tile is one of those virtual ops that we use to encapsulate the concept of virtual tile allocation that we need to take care of. Right, so just to quickly summarize, this is only tip of the iceberg. Diego hinted that this technology can do much more. We focus on mask vectorization, but there are other vectorization strategies that we didn't have time to cover. We also didn't dive into the drivers that we've been using, namely ERI and transform dialect, that would deserve a presentation on their own. I mean, there have been presentations, so please do watch them. Also, we're hoping that this convinces you that this framework is very flexible and very powerful, and you can achieve a lot with not so much effort. I mean, it is challenging, but when you think about how complex scalable vectors have been and how much time we spent adding support for them inside this framework, it's quite impressive. So thanks very much for listening.
Okay, I have a question here. In your talking about the lowering to SME dialect, I wonder, SME has SME 1, SME 2, and the instruction is growing. And I wonder whether in your framework you have some place to record the characteristics of the instruction so that you know where your lowering stop. You don't want to further decompose it, and then you have to reconstruct it. Because reconstruct it is really hard, right? I mean, everything is broken. This example you show here, obviously you have a very good understanding of the what is the instruction, MOPA instruction. So you know it. You know you come here, you just stop here, and then that exactly map to one instruction. It gives you an outer product. My question is that in your framework, do you have any other place? I mean, you cannot just do it by hand, right? I mean, some other places to describe the machine, describe the ISA so that your lowering can stop there, you know?
That's a very good question. And yes, there's SME1 and SME2. We are focusing on SME2 because that seems to be most popular, or there's most interest for SME2. But there's also a lot of extensions, and the extensions enable or disable certain variants of the MOP-A or outer product instructions. So you're right, we need some mechanism to be able to make sure that we don't generate instructions that are not supported if a certain extension is not enabled. There is no infrastructure or logic for that yet. That's on a to-do list. But yeah, it's going to be quite important, I agree.
Okay, thank you.
Sorry, can I ask a question?
Yes, but quick.
Just one question. Okay. So you mentioned a couple of times that the MLIR level, there's no way to manage the virtual tiles and so on. So, and I think it's important to be able to count the virtual tiles that you're going to use and have a cost model of allocating these things and controlling how many. And in extension, I guess it extends to SVE vectors too. So is there a plan for that, and whether to do it LLVM or add more general just allocation logic in MLIR?
This is also a very good one. So basically, this is a very elaborate matrix multiplication engine. It can do other things as well. But we look at how we can optimize usage for that particular scenario, and that informs the kind of tiling that we want to do. And this is what we think. But if you want more generality, then yes, you would need a cost model, because for a matmul, we can just sit down and write what the distribution or what the allocation should be. Should we be using SME for something more general? I mean, obviously we can do other things, but I mean,